Hello everyone, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Gandhinagar. I am the subject matter of Power System 2 subject, which is in the 5th sem Electrical Engineering, and GTU subject code of this subject is 3150911. Students, we are in chapter number 7, and this is the second chapter for so this is the second lecture for this chapter. In previous lecture, we studied about basically what is corona, and the derivation for the critical disruptive voltage, and the advantages and disadvantages of the corona in the previous lecture. Now this is the second lecture for chapter number 7, and the topic number 3 is critical visual voltage. Now first of all, we studied about critical disruptive voltage. So critical disruptive voltage is a voltage at which the potential gradient created from one conductor to other conductor, and due to that charges will transfer charges will try to transfer from one conductor to other conductor, and if there is moisture is present in the air, then breakdown will occur easily, because moisturized air will support the corona. So critical disruptive voltage is a voltage at which corona start forming, and critical visual voltage at which corona will appear. So this is the difference between critical visual voltage and critical disruptive voltage. So basically the mean phase neutral voltage means at which means the minimum phase neutral voltage at which the corona glow appear, means a faint violet color means corona appear surrounded to the conductor. So that voltage, that minimum phase to neutral voltage is called the critical visual voltage at which the corona appear, means start up, we can visualize the corona. So that voltage is called the critical visual voltage, and it is denoted by VV. Now from the definition of both the voltages, we can easily say that critical voltage is greater than the critical disruptive voltage, because this is the voltage at which corona start forming, means the process is start, and this is the voltage at which corona will appear. So this is the initial means process, and this is the final process, means so that's why we can say this voltage is smaller compared to the VV. And whenever the breakdown occur, the ionization will occur, and so that the corona will appear. So this is the whenever the breakdown occur, at the time the voltage is VD, and whenever the ionization occur and corona appear, it is called the VV. So from this we can easily say that visual critical voltage is greater than the critical disruptive voltage. Now generally breakdown voltage is attained at a distance of say r is the radius of the conductor, 1 plus 0.3, this is the current density into the radius, under root delta into r. From the axis, generally instead of r, so in other words we can say that VV is 1 plus 0.3 by delta r times the VD. So here you can see that this VV is this times the VD. Now so we can write the equation VV is equal to VD into 1 plus 0.3 divided by delta R. So just put the value of means that we derived in the previous lecture, VD. So R into delta into G0 MV ln D by R into this is 1 plus delta under root delta R. So if we solve this, we'll get the G0 MV delta R. So these are the common terms, and 1 plus 0.3 under root delta R ln D by R. Now the visual critical voltage is 2.11 MV into delta into R 1 plus 0.3 delta into R under root ln d by R. The These voltages are in kV, and this is the RMS value of the visual critical voltage. Now in this visual critical voltage expression, this MV is the roughness factor. So as we already gone through the previous lecture, in previous lecture we discussed about the surface of the conductor. Means if the surface of the conductor is rough, then corona will glow brighter, and if the surface is smooth, then corona will appear but it will not glow brighter. So this MV is the roughness fact MV is the roughness factor. So here it is multiplied with the other terms. So the range of the MV is mentioned over here. So it is roughness factor, so it is 1 for the smooth conductor. If we use smooth conductor, then keep MV is equal to 1. Means take MV is equal to 1. MV is less than 1 for the rough or stranded wire. Means if we use number of wire and surface is also rough, then take MV is less than 1. And MV is 0.98 to 0.93 for rough conductor, which is conductors which are exposed to the atmosphere severities. Means whenever mm, the snow strikes and then rainy season, so for that take MV is between 0.98 to 0.93 for the rough conductor which are exposed to the atmospheric severities. So this is the value for MV, and 0.72 for the local corona on standard conductor. So local corona in the stranded conductor. So these are the values for MV that we use in the examples. So please keep in mind the values of MV, and you can also note it down for the example calculation. Now this is the topic number 4 in this chapter, corona power loss. So whenever the corona occur, at that time we need to give additional voltage to fulfill the voltage sending end to receiving and voltage ratio. So basically power loss is due to the corona under means fair weather. If weather is fair, at that time PC means corona power loss is equal to 244 F plus 25 divided by delta under root R by D VPH minus VD whole square into 10 raised to minus 5 kilowatt per kilometer per phase. So this is the peak formula. Now in this, VPH is the voltage per phase in kV, VD is the disruptive voltage, means this is the critical disruptive voltage in kV, F is the frequency is in hertz. So this is the power loss equation. Now uh, generally the factors like rain, then sleet means snow, which means barf ke ole girna like sleet, and fog may reduce the disruptive critical voltage VD to 0.8 VD. So whenever such atmosphere means in such kind of atmospheric condition is there, at that time that condition will yeah, this condition will support the corona formation. So at that time the disruptive voltage which are required is to 0.8 VD, and corona under abnormal condition of the weather, the equation of the power loss PC will become P dash C. So it is 244 F plus 25 divided by delta, then R by delta, this term is common, then VPH minus see in this previous you can see that VPH minus VD. So we are taking VD over here, VD taken over here is 0.8 VD square. So we are just placing the value of VD over here. So VD square into 10 raised to minus 5, and the unit is kilowatt per kilometer per phase. Again, here we use Peterson's formula, which holds well when the ratio means VPH by VD is less than zero point 0.8. Then we can use the Peterson's formula. Then Peterson formula states that the power loss PC is given by then the equation will become PC is equal to this you need to mug up for the example calculations. 21 into 10 raised to minus 6 into f into vph square. We solved this equation, this one and the previous one, and in the denominator log 10 d by r square into k. This k is the means the ratio which we use vph by vd, and for different value of k, this is the table which is drawn. Means if this k varies with the vph by vd, means per phase voltage to the disruptive voltage. So here the ratio of vph by vd is mentioned in the table. So it is starting from the 0.6 to 2.2, and for this the value of k is different. So it is nothing but the ratio of response of means Peak's formula and Peterson's formula. From this we can have the value of k means according to the vph by vd ratio. So the power loss due to corona depends upon the k. From this we can say that if k increases, power loss due to corona will increase. So the ratio of k is starting from the 0.012 and it is to 8.0. So for different value of k, vph by vd is ratio shown, and from this equation we can calculate the power loss due to the corona. So you need to mug up this equation for the example calculations which we calculate after this topic. Now the fifth topic is a line design based on corona. So line design based on corona, generally the corona loss produces the undesirable effects which are power loss and radio interference. In the HV transmission line and substations, generally such kind of radio interference occur, and this is just because of the corona. And depending upon the potential gradient at the conductor, that will produce the corona, and due to this corona radio interference will occur in the HV transmission line as well as the substation. Now radio interference generally basically influenced by means all those factors which influence the corona, like the radio interference means influenced by the air density. Means if the moisture is present, then density of the air is more, and if there is no moisture in the air, then the air density is less. So according to the weather condition, then humidity, it is again associated with the weather condition, then wind, contaminants, etc. Means generally we use such resources to find out the radio interference. For the bad weather, radio interference is 10 to 25 dB higher, so that will produce more noise. And for the fair weather, means for the fair weather comparison, the radio interference is 10 to 25 times 10 to 25 dB more or higher than the fair weather. And partial discharge across conductor, and due to that spark occurs, means spark across the gap will generates. And some of the factors, these are the factors which owes the radio interference. Now radio interference effect carry the consideration carry in the consideration for the EHV line of 200 kV, 220 kV and above. So generally for such kind of transmission lines, basically RI will occur, and RI is inversely proportional to the radio frequency. So radio interference basically proportional to the radio frequency. So therefore service of very high frequency bands such as TV, then radar, then microwave, and FM broadcasting are not affected, because RI is basically inversely proportional to the frequency. Frequency is higher, radio interference frequency is less. So such for such devices and for such technologies we generally use higher frequency. So higher frequency is there, so radio interference is less. Now by using the bundle conductor, surface voltage, stress, corona and radio interference, that will means that can reduce the radio interference. Means if we use the bundle conductor, or that will minimize the surface voltage, stress and corona and radio interference. It is advisable to use bundle conductor to minimize such problems. uh, Now this is the sixth topic, it is corona loss measurement. Now this is the corona cage through which we transfer a wire. A supply is given to this wire, and a core is the means the cage is connected with the current meter. So this cage is made up of metal cylinder. Now generally ion produced by the electric field, that will results the space charges moves around to the conductor, and whenever the space charges moves around to the conductor, means energy required for the charges to remain in motion. Means once the charges moves around in the conductor, it requires more energy to rotate for the particular shape and for the particular area, is derived from the supply system. Now generally the power loss occurs in the space surrounding to the conductor. It is necessary to supply the additional loss from the supply system, and this additional loss is called the corona loss. And this additional power loss is referred as the corona loss because for the power loss, whenever the power loss occurs in the space, means surrounded to the conductor, then it is very necessary to supply the additional losses from the supply, because ultimately the consumer will suffer from the lack of power or less amount of power. So this additional power is referred as corona, and since this phenomena is resistive, so it is independent from the power factor, and the measured power will be VI watt because it is independent from the power factor. Now these are the methods by which we can reduce the corona, because corona is nothing but the loss. So loss of the power. So generally the first remedy to reduce the corona is by increasing the diameter of conductor. So as we increase the diameter of conductor, means R is equal to rho L by A. So R is the radius. If we consider that radius in the diameter, then it is d by 2. So generally as we increase the conductor diameter, so cross sectional area of the conductor will also increase. And if cross sectional area of the conductor will increase, then the resistance of the conductor will also increase. So from that we can say that R is equal to rho L by A. So diameter of the conductor will increase, A will increase, so as the R will decrease. Now the second remedy is we can increase the spacing between conductors, but when we increase the spacing between the conductor, the cost of the supports, means as the spacing between two conductors are high, so support structure will also change, and the cost of the support, means cross arm, will increase as we increase the spacing between the conductors. Now this is the topic number 7, means examples based on the corona. So such kind of examples are repeatedly asked in the GTU exam. So I mentioned the two most IMP examples for this chapter, so please pay attention over here, and means if you have any query and doubt, then you can personally call and message me till this topic. Now example, first example is a three phase 220 kV 50 hertz transmission line. Means transmission line having the voltage capacity say 200 So the line voltage which is given 220 kV, and the frequency of the transmission line is also mentioned. So F is equal to 50 hertz, and it is consisting of 1.2 centimeter radius conductor. So the diameter will become 2.4, and uh, it is spaced 2 meter at the corners of an equilateral triangle. So it forms the triangle, and they are separated by 2 meter with each other. And calculate the VD, means disruptive critical voltage between the lines. Regularity factor is equal to 0.96, so it is M0. And the temperature, which is 20 degrees centigrade, so T is equal to 20 degrees centigrade. So the barometric pressure is 72.2 cubic meter cm of the mercury dielectric strength of the air, which is also given. G0 is 21.1 kV RMS per centimeter. So this from this you can write the data given, and these are the data given through which we need to calculate the VD. Now the equation for VD that we derived is G0 delta M0 R ln D by R. So here delta is unknown, so air density factor that we gone through the previous theory, that delta is equal to 3.92 B by 273 plus T. So this is the standard equation, and if we know the B and T, then we can calculate the delta. So here we have the value of B, that is 72.2. So over here you can see that this is the barometric pressure which is given in the data, and T is the we can say temperature. So temperature is also mentioned over in the data given. So from that we can calculate the delta. So delta is equal to air density factor. So air density factor is 0.966, and for that we can now we have this delta, so we can write the equation for the VD. So VD is equal to G0 delta M0, then R ln D by R. So here we are placing just values of all the data given, means these are the values which are given in the data. So from that we can calculate the VD. So VD is 120.1 kV RMS. So this is the RMS value, so we need to convert this means line to line voltage, means VD is equal to root 3 into V. So root 3 into 120 into 1, so that will be 208 kV value RMS. So this was the phase voltage, this is the line voltage, so that's why it is multiplied with the 3. So this is how you can calculate. This is the basic example related to the visual critical voltage. And now we'll see the some different example having more weightage, and need to find more things from this example. So this example states that 110 kV, means it is our line voltage 110 kV, 50 hertz is the frequency, 175 kilometer long, means it is the distance. The transmission line consists of 3 lines of 1.2 centimeter diameter, means here we have the 3 lines having 1.2 centimeter each diameter. Copper conductors placed in a 2 meter delta arranged. Assume, means 2 meter delta is the line spacing. Assume that temperature is 25 degrees centigrade, barometric pressure and 74 centimeter cubic meter is the barometric pressure, is the 74 cubic meter. And assume surface irregularity is factor is M is equal to 0.85, and it is depending upon roughness of the conductor factor. And MV for local corona, MV is 0.72, and MV for the general corona is 0.82. So these are the data given, and these are the points that we need to calculate. First is VD, then critical visual voltage, then visual corona, and then power loss due to the corona using Pick's formula. under fair weather and wet weather condition. Now the solution, so first of all we start with the conductor diameter. It is given 1.2 centimeter. So here we are converting d to r is 0.6. So spacing of conductor d is equal to 2 meter for 200 centimeter. Okay, now here you can see that this is the first step. Now the dielectric strength of the air G0 is still unknown, so we can calculate 30 by root 2 kV per centimeter, and it is RMS assured. Now biometric pressure B is given 74 and temperature T is equal to 25 is given. So irregularity factor for the particular condition, over here you can see that M0 is 0.82 and 0.72 for different weather condition. So and surface of the conductor, so mv is equal to 0.73 for the local corona and mv is equal to 0.82 for the general corona. Now operating voltage vps is equal to line voltage divided by root 3, so it is 63.51, and air density delta is equal to as you already gone through this equation, 3.92 plus b and 273 minus b, sorry, plus b. So when we place the values of b and t over here, so you can calculate the delta. Now from the value of delta you can calculate the vd. So equation for the vd is g0 m0 delta into r into ln by dr. So this r is spacing between two conductors and this is the radius of the conductor, so no need to get confused. So g0 is 30 by root 2 into m0 is 973 into 0.85 into 0.6 ln. So the value of the d is 200 and r is 0.2. So from that if we calculate this, we can find out the value of vd, and vd is equal to 61.15 kV rms. Now the second point is that we need to derive VV to neutral for local corona. So here VV is equal to VVL means local corona. So this is the equation for the VV, and here we are placing all the values over here. So VVL is equal to 7.71.99 or 72 kV RMS. Now the third point VVG, so visual critical voltage to a neutral for general corona. So in the previous case we have the local corona, now it is general corona. So VVG is equal to 72 what is 72? 72 is the see we can see the in the previous slide. So here 72 is for local corona, so 0.72 is for local corona. So just we are replacing all the values, means g0 is 30 by root 2, then mv is 0.72, delta is 0.973, then r is 0.6, and 1 plus 0.3 by 0.973 into 0.6, and ln 200 by 0.6. So vv ultimately 71.99, and it can be right 72 kV rms also. Now if visual critical voltage for the neutral for the general corona, so here vvj is written. Now these are the values which are given, so we are just placing the value and we can find out the vvg, and this is in the rms. Now power loss due to corona, this is the d topic of this example. For the fair weather condition, according to the PICS formula that we already gone through the previous theory. So PC is equal to 244 by delta F plus 25 under root R by D, and VPH minus VD square into 10 raised to minus 5 kilowatt per kilometer per phase. So we are just placing all the values and we can find out the PC. So all the values are placed like this, and PC is equal to 57.86 watt per kilometer per phase. So total corona loss for 175 kilometer long three phase line, so we are just multiplying this with the distance and the phase. So 75 multiplied by 3 into 57.86 watt, so that this will become 30.38 kilowatt, and this are the power loss due due to the corona for stormy weather condition. So for that it is v dash d is equal to 0.8 vd, and vd is that we calculated over here with the help of this equation. So the VD is 61.15, so we are just placing all the values 68.50 in this 61.15. So the VD dash will become 48.912. So after that, the total corona loss for 175 kilometer three phase line according to the PIX formula. So we are just here placing the values again. So according to the PIX formula, all the values are mentioned over here that we already studied in the data given section. So if you solve this, you will get the PC is equal to 1152.5 kilowatts. So this is the corona loss whenever the corona occur, and we need to maintain the terminal voltage, means receiving end as well as the sending end, then we need to control this. Now this is the means last session of this topic, means worksheet questions and assignment questions both are written in this slide. So for the first of all the worksheet question. First question is, what is the difference between critical disruptive voltage and visual critical disruptive voltage? Then second question is, what do you mean by the conductor roughness factor, also how it affects the corona? And assignment questions are, explain the corona power loss with suitable expression, also explain the method to measure corona power loss. And the second question is, explain the design based on corona, also enlist the members for the reduction of the corona, and examples means which we already calculated in this presentation, that you need to write in your assignment booklet or assignment paper. Now the related instructions are written below the assignment question and worksheet questions. Note down this all these questions, and you can take the snap of these questions. Now if you have any query and any doubt, then you can contact me, and you can call me, feel free to call me. And if you have any means suggestion about this, then you can share it with me. Also means after this presentation, means you need to write the assignment, you need to submit the full assignment, because this is the last topic of this chapter. So thank you very much, student. Thank you all. If you have any quick query or any doubt after this presentation, so please call me, and you can WhatsApp me. Thank you very much, student. Thank you all. Jai Swaminarayan.